Okay, I want to start the presentation. My name is Mina Jansen. I am one of the technical editors from the Open Charge Alliance. And in this webinar, I want to talk about the transaction mechanisms in OCPP, mainly focusing on OCPP 1.6 and 2.0.1 and the differences between them. Here is my personal information. And this is the agenda for today. So first I want to quickly go over some of the differences between OCPP 1.6 and 2.0.1. Then I will focus on the transaction mechanisms of the respective versions. So for 1.6 and then for 2.0.1. And the main differences which have been made in the transaction mechanism of OCPP 2.0.1. After that, I will quickly go over some configuration settings that have impact on the transaction mechanism. And then I want to also quickly talk about the fixed cable because this also has some impact on the transaction mechanism. And finally, I will give a short simulation of the transaction mechanism of OCPP 2.0.1. So first, I want to talk about some differences. OCPP 2.0.1 is quite a bit larger than OCPP 1.6, but this does not mean that it is far harder to implement, because what we've done is we added a lot more explanation, added a lot more detailed requirements, and we added extensive sequence diagrams that clearly show the message flows between the two systems. We also added a lot of new functionalities, but not all are mandatory to be implemented. They can be implemented when they're needed. And we also improved the existing functionalities to be more flexible to support more business cases. So this gives a lot of more flexibility to the whole protocol. This last part is also what we've done for the OCPP 2.0 transaction mechanism. But first I want to go over the transaction mechanism of OCPP 1.6. This is because to give a bit of a reference before I start talking about what we've done with 2.0.1. And this is the transaction mechanism of OCPP 1.6. A transaction can have multiple energy transfer periods, and a transaction starts when both the EV is connected to the charge point and the EV driver is authorized. And a transaction will stop again when one of these conditions is not the case anymore. I hope it's a bit readable, but I will go over this sequence diagram. It shows the complete transaction message flow between the two systems. First, the EV driver plugs in the cable in the charge point, and it will send a status notification with states preparing to the central system. Then the user authorize. This can also be in a swapped order. After both conditions are true, the transaction starts and the charge point will send a start transaction message containing the connector ID and the ID tag. Then the energy offer starts. The charge point can report a status notification for this with status charging. Then the user can stop the transaction again by, for example, swiping an RFID card, but this can also be a stop button, for example. Then the transaction stops. The charge point will send the stop transaction message with reason local if it was a locally stopped by the EV driver. Then the energy transfer stops, and the charge point will send a status notification finishing. And then after the cable is being unplugged by the EV driver, it will send the status notification request available again. Next, I want to talk about the transaction mechanism of OCP 2.0.1. We've done two major changes. One is that OCP 2.0.1 now has one universal transaction message, which contains all transaction-related data from all the OCP 1.6 transaction-related messages, but also some more. And we've made the start and stop points of the transaction configurable. First, I want to talk about the universal transaction message. I've created a table which displays how the OCP 1.6 messages on the left side are mapped to 2.0.1 on the right side. So if you look at the 1.6 table, you can see start and stop transaction, and this is mapped to the transaction event, and start transaction will have event type started and stop transaction will have event type ended. So one of both transaction events of this type are sent during a transaction. Then the meter values, the transaction-related ones, so the sampled meter values, are also provided in the transaction event message, and that can be with intermediate transaction event message with event type updated. The non-transaction related meter values, so for example, the clock-aligned meter values sent outside the scope of a transaction, can still be sent with a meter values message in OCP 2.0.1. The status notification message in 1.6 provided multiple kinds of information. It's transmitted both the charging state of the charger and the connector state. So if a connector is available or occupied. In 2.0.1, this has been split. So the transaction the charging state will be reported in the transaction event, and the connector state will still be reported by the status notification message. These are all the fields contained within the universal transaction event message. I want to quickly go over the important fields. These first two I already mentioned in the previous slide. So the event type started, updated, and ended, and the meter value. This is the transaction ID. This is also an important change that has been made in 2.0.1. Now the charging station is responsible for generating the transaction ID instead of the CSMS. This decision has been made to make offline situations easier for the implementers when you have to queue transaction messages. But it was also more logical because the charging station is also responsible for maintaining the transaction. The transaction events now also bear a mark if they were queued when the charger was offline, and it is no longer required that transaction events are transmitted to the CSMS in chronological order. And they all received a sequence number, which will incrementally increase, and this way the CSMS can verify whether it has received all transaction event messages after the transaction event with event type ended has been received. The trigger reason field contains a list of trigger events which can trigger a transaction event message to be sent. This is the list of possible values. These are not all mandatory. There are also some conditional values. So for example, energy limit reached. This value is only used in prepaid charging solutions. So if you're not using get business case, then you don't need that value. There are, of course, mandatory values which are stated in the specification by requirements. So if you look at the top, the most used ones are the authorized, the cable plugged in, and the charging state changed. Here I'm going to talk about the charging state. These are the possible values for the charging states. These can be reported when a charging state changes, and this is also what I was talking about when talking about the status notification message for OCP 1.6. This is an example of a case that a status notification would have been sent. And so, for example, with status charging, but in OCP 2.0.1, this would be a transaction event request with charging state charging. The ID token contains all authorization-related data. This field only needs to be included after in the first transaction event request after an authorization has been done. And the EVZ data type contains both the EVZ ID as well as the connector ID, and this field only needs to be provided in the first transaction event after the cable has been plugged in. Well, if after the EV and the EVZ are connected, it does not have to be a cable. The stopped reason field only needs to be provided in the last transaction event request message with event type ended. This is a similar field to the reason field in the stop transaction message from OCP 1.6. So a lot of these values are also similar. These are also not all mandatory. The most commonly used ones are local and remote, which are the same as the ones in OCP 1.6. So local for a local stop by an EV driver and a remote by a request stop transaction from the CSMS. Now I want to talk about the second change in OCP 2.0.1 transaction mechanism, and that's the configurable start and stop points. These are the start and stop points that can be configured. Multiple of these values can be configured at a time, and these values need to be viewed as a condition. So for example, if you would configure EV connected as start point, then the transaction will start when the EV and the EVZ are connected. And when this is not, if you would configure the EV connected at the TxStopPoint, then the transaction will stop when the EV and the EVZ are no longer connected. We are aware that making this configurable will make the transaction mechanism far more complex, but there are two ways to make it less complex. And for that, I want to have a quick view at the TxStopPoint configuration variable. This is much like a configuration key from 1.6, but then mapped to the 2.0.1 device model mechanism. I will tell something a bit more about this later during this presentation. But for now, I want to have a quick look at this part. If you look at the bottom value, so the value list, you can see that the charging station does not have to support all values. In this value list, it can report which values are supported, so the CSMS knows which values it can configure. So from this list, you can choose which values to support. The second way to make it less complex is to make the mutability read-only. An implementer can choose whether he wants to make it read-only or read-write. And when making it read-only, you can pick your the values you want to support, and the CSMS won't be able to change it. And then you will have a static transaction mechanism once again. If you have a 1.6 charge point and you want to have an easy migration to 2.0.1, then you could make the decision to make the transaction mechanism as similar as possible. And you can do that by, for example, configuring power path closed for the TxStopPoint and authorized and EV connected for the stop point. and you can even also make the mutability read-only. So in this case, you would have a very easy transaction mechanism. But the reason why we made this configurable is to support more business cases. So for example, if you want to calculate idle fees, so you want to increase the scope of your transaction and stop the transaction after the EV driver has actually left. You can do this by, for example, configuring parking bay occupancy for both TxStart and StopPoint. If you have a parking bay sensor. Otherwise, you can also do EV connected. In that case, the EV driver will pay for idle fees as long as the car is connected to the charging station. The last part of I want to talk about before proceeding to the next topic is the mutability, how to make the decision between read-only and read-write. You need to ask yourself the question, what do I need? Do I have one client which only supports one business case, or multiple that want the same business case? In that case, you can make it read-only, configure the values that you need. But if you have multiple clients which all have different business cases, then it may be interesting to look at making it read-write and support as many values as possible, because then you don't need multiple firmwares for the different transaction mechanism. Then you can just use the same firmware type and configure the different values that you need. Now I want to have a bit of an in-depth look at the messages being sent between the systems based on the configured start and stop points. First, I want to have a look at the start point. So for example, when EV connected is being configured. So you can see that the EV driver plugs in the cable, it reports a status notification with status occupied, and then the transaction is being started with a transaction event with event type started. Because the cable has been plugged in, you have the trigger reason that states that the cable is being plugged in. You can report the charging state as EV connected and provide the information of the EVZ ID and the connector ID. Then there are several other transaction event messages sent in the transaction based on the trigger event. So for example, when the user authorizes itself, then you'll get a transaction event with trigger reason authorized. And after the energy transfer has been started, the charge point sends a transaction event with charging state is charging. But what if we would configure authorized as the start point? In that case, the first transaction event message is not sent because it will start when the user authorizes. Then the second transaction event will become the first one and will receive event type started. But it also needs to provide the EVZ ID and the connector ID, because this is now the first transaction event sent after the cable has been plugged in. Now I want to have a look at the TxStopPoint. So here also is the EV connected set as a value. So this means the transaction is stopped after the cable has been unplugged. So here you also have several transaction events. The last one is the transaction event with event type ended. And if you would configure authorized, then all transaction events after the stop authorization will not be sent anymore, because this will become the last transaction event with event type ended, and the last transaction event also needs to contain the stopped reason, which in this case is local because it was stopped by the EV driver. Now I want to have a look at the configuration settings. In OCPP 1.6, key value pairs were used. I've shown here an example of a configuration setting which is still exists in both 1.6 and 2.0.1. So the key would be the connection timeout, and value can be configured to a number of seconds, 60 for example. In OCPP 2.0.1, the device model is used, and this is built up of components and variables. Each component contains one or more variables, and there are two kinds of components: physical and controller components. Physical components are hardware components, which can be configured to monitor, for example, and controller components contain configuration settings, like the configuration keys from OCPP 1.6. I want to have a look at the controller components. This is the configuration variable, which is equal to the configuration key I've shown in previous slides, the EV connection timeout. It is linked to the component Tx controller. This is the controller responsible for harboring all transaction-related configuration settings. And for the rest, is the information in this is the same as the one from OCPP 1.6, but it contains a bit more information about the characteristics of the configuration setting. These are the two components I want to talk about. The left one I already mentioned, and the right one is the auth controller. This contains all configuration settings for the authorization, which is also important for the transaction mechanism. The Tx controller also contains the TxStart and StopPoint I already talked about. And I've also listed all other required configuration settings, variables, which are linked to these components. And I want to mention them briefly because these have impact on the transaction mechanism, and you have to be aware of that. There are also some optionals, but they don't need to have to be implemented, but I also recommend to have a look at those. Okay, so the start and stop point are already mentioned. The EV connection timeout, most of you are familiar with this one. This field is used to configure how long the charging station will wait before deauthorizing the transaction after the cable has not been plugged in. The following one is stop Tx on EV side disconnect. This will tell with a Boolean value, true or false, whether the transaction is not allowed to resume again after the cable has been disconnected from the EV side. The stop Tx on invalid ID is stating whether a charging station needs to stop the transaction after it already started it and started charging, but then it noticed that the CSMS is telling it that the identifier is not valid anymore. This could be the case, for example, if it started offline, or if it cached the ID, but the status changed during the period it was cached. For the auth controller, these are some variables which state whether it's possible to do offline authorizations and whether it is allowed to use the cache or the local authorization list to authorize a transaction. Now I want to briefly go over the fixed cable. OCPP always assumed that the cable was detachable on both sides, but there are a lot of charging stations in the field that have a fixed cable on the charging station side. And now OCPP 2.0.1 also supports this case. So it clearly describes how to handle the fixed cable. But the reason I want to mention it today is because there are two scenarios where the transaction mechanism is actually different than when you're not having a fixed cable. So if the cable is detachable on both sides. The first scenario is this one. I don't think it's very readable, but I will go over it. This is the case when the stop Tx on EVZ side disconnect is false. So this was the configuration setting that is used to indicate whether the transaction may resume after the cable is unplugged at the EV side. So the cable is plugged at the EV side. If it replugs the cable, the situation with both fixed cable and detachable cable is the same. But when you want to stop a transaction, there's a difference. So if you look at this part, this is for when you have a detachable cable. The user needs to authorize again to unlock the cable and then unplug the cable to make the charger available again. But in the case you have a fixed cable, then a timeout has been implemented because we cannot be sure that the EV driver actually returns because it does not need to retrieve its charging cable. The second case is also for when the cable is unplugged from the EV side, but now it is not allowed to resume the energy transfer again. The whole alternative block is for when you have a detachable cable. So it needs to be unlocked and unplugged. But in the case you have a fixed cable, the charger will immediately proceed to reporting that the connector is available again. Now I want to proceed to the questions for this part of the presentation. After this, I will resume to showing a simulation of the transaction mechanism.
Thank you, Milan. Let's see. If people have questions, please use the questions box. Let's see if there are any questions yet. Let's see. Can I still use OCPP 1.6 when the charger is equipped with a fixed cable?
Yes, that is of course possible. It is described a bit less, but the certification program takes this into account. And what happens is that status notifications are sent a bit differently. So you have the status notification finishing and the status notification available, but often it will proceed a bit quicker to the available state, because when the connector is unplugged on the EV side, then the charger will often report that it is available again.
Okay, thank you. Let's see. What is the effect of the energy transfer TxStopPoint when charging is temporarily suspended due to load balancing? And will that stop the transaction in that case?
Yes, we discussed this during the technical working groups. Energy transfer and power path closed are not really recommended stop points. The values are shared, but the most commonly used stop points are more the authorized or the EV connected. So EV disconnected and stop authorized, and not the energy transfer and power path closed stop points. Those are more for the starting of a transaction, meant for that part.
Okay.
But the answer is yes. It will stop the transaction when it's spent.
Okay. Let's see. And do we need stop Tx on EV side connect if TxStopPoint is EV connected?
Sorry, do we need to stop on the? Can you repeat, Martijn?
It's a code, I think. Do we need? And the code is stop Tx on EV site connect. If other code TxStopPoint is EV connected.
Well, okay, if the stop point is EV connected, then the transaction will need to stop when the EV and the EVZ are no longer connected. I think that was the question.
I certainly hope so. Let's see if we have, do we have time?
Yeah, I think we have some time.
Okay. One moment. If I have a combination of 1.6 and 2.0.1 charging stations, will their behavior of 2.0.1 be exactly the same as 1.6 if I start the start-stop points right?
It will behave mostly the same because a lot of the OCP 1.6 transaction mechanism has been incorporated in 2.0.1. But of course, you need to send the transaction event messages, and that is a bit different than how you would do it in 1.6. So I cannot say for sure that your whole state machine is the same. I don't think so, but you can make it quite similar.
Oh. Okay. Let's see if this one can. Is there a way to identify the cause of suspended EV, battery full or too hot, etc.?
To report this kind of information, I would use the device model. There you can configure hardware components, and those components can report this kind of information themselves. So that will be separate but linked, because when you're reporting something with the notify event request, you can also provide a transaction ID in the message, so you can link them to the transaction. So you can mention that the battery was too hot in that separate message. So it's not inside the scope of the transaction event, but it can be reported in sync with another message. I think that's use case N07 and 08 you have to look at.
Okay. Let's see. Well, we will still be able to answer questions after your next demo, I think.
Yeah, I think there's still time after.
Yeah, so if anybody has any questions left, please ask them in the questions box, and Milan will get to it later on. Now we will begin the second part, the demo. Milan?
Yeah, so I want to show a simulation I created for the transaction mechanism. This has helped me a bit to understand the transition to certain OCPP communication states and which actions can be performed in certain situations and what impact they have on the transaction mechanism. So here I've created a model in Enterprise Architect. I hope it's a bit readable. I will zoom out a bit to give you an overview. So this is the model I created. I will zoom in a bit. So I will start at the top. If you look at this box, I have configured all kinds of settings. A lot of these settings are similar to ones I mentioned during the presentation. So some configuration keys, stop points, and these all have impact on the flow of the simulation of the model when I walk through it. So when I start the simulation, it stored all the configuration items, and it will start in the idle state. So this will be the first state. In this model, I tried to merge both the charging state as well as the authorization in combination with the TxStart and StopPoints. Based on all these variables, the flow will be different, and I tried to do the naming based on those values. So in this case, idle state refers to the charging state. So the charger is now idle, and we can proceed with sending certain trigger events. These are not really readable, but I will mention what I can do. I can proceed to that the EV entered the parking bay, so then it will proceed to the parking bay occupied state. This is an optional state because it is possible to skip the state or not implement this state. So I can also leave the parking bay again, proceed to idle. I can start the interaction with the EV driver. I separated this, but it is still in the idle state. Now I can choose between connecting the EV or authorizing using a local start or a remote start. I can do this in either order. So I will proceed with connecting the EV and EVZ. Then it proceeds to the EV connected state. And if I proceed to the local start, it will go to authorize. I've configured whether the identifier is true or not. Then it will proceed to has authorized when the identifier is true. And if both authorized and connected are true, then it will proceed to power path closed, and then immediately will proceed to energy transfer if both the EV and EVZ are ready for energy transfer, which I've configured to be the case. So it will do a local start, then it will walk through the diagram and end up in the energy transfer started state. From this point, you have several options which can be done. The charging rate can change, but it does not really impact the states. The EV or the EVZ can be suspended. So for example, the EV suspends the energy transfer for some reason because the battery is too hot or some other reason, and then it will stop the energy transfer, power path close, and proceed to the suspended energy transfer state. And from this state, I can proceed to interacting with the EV driver. I will have several options. The EV driver can stop the transaction, for example, with an RFID card, or a remote stop can be sent, or the cable can be unplugged on the EV side. I want to unplug the cable on the EV side to simulate also the business cases from the fixed cable I just mentioned. So I will unplug the cable on the EV side. It will proceed to EV communication lost. And then you see that I have configured that the transaction is allowed to resume. So it is still authorized, but the cable is not connected anymore. And now I have to replug the cable before the connection is being timed out, configured by the connection timeout configuration setting. So if I reconnected before, I lost my triggers. Okay. So I connect the EV and EVZ again, then I can resume the energy transfer, but it is still configured that the EV is not ready. So I have to click that the EV is ready again, and then it will proceed to energy transfer started. And based on, as I mentioned, based on all these settings, you will walk differently through the states, or based on the trigger events you trigger, that will also have impact to which state you go. I will go briefly over the parts I did not reach in this flow. And that is, for example, the stop authorize and the deauthorize state. So, for example, if the energy transfer is started and the user stops, or the charging station receives a request stop transaction, it will go to stop authorize, and then it will go back to this part, and then EV has connected will be the state, and has authorized will not be active anymore. And then you can unplug the cable to go back to the idle state. I can briefly show it, why not? So start interaction. I will first do a local start to simulate that it now has authorized. Connect the EV and EVZ. Will proceed to energy transfer started. Then I will start the interaction. I will do a local stop. It will go to stop authorize. Energy transfer stopped, power path opened, and now it's in the EV connected state. And if I disconnect the cable, I'll be back in the idle state. Okay, this is what I wanted to show. This helped me a lot with understanding how the transaction mechanism works and what is possible. Just a bit better overview in combination with the test cases I'm writing for the transaction mechanism. Okay, now I want to proceed back to the presentation. I think we have a little bit more time for questions. Martijn?
Yes, I'm sorting them out. Let's see. We have some questions regarding your first part of the presentation.
Yeah, that's fine.
If EV connected is not in stop point, will stop TX on EV side connect is true. What does CP should do when EV disconnected?
So if I understand correctly, when EV connected is not configured as start point, but is configured as stop point?
Ooh, let's see, the code is while stop TX on EV side disconnect.
Oh, stop to the configuration setting, yes?
True.
Stop TX on EV disconnect is true. Yeah, that configuration key speaks about the authorization of a transaction. So if a transaction is deauthorized, it does not necessarily stop the transaction. It is just not allowed to proceed until it receives a reauthorization. The TxStopPoint is the one declaring whether the transaction will actually stop. So whether the transaction event request with event type stop ended, sorry, is being sent. So that key will only say whether you need to reauthorize.
Okay. Let's see, questions are coming in rapidly now.
Okay,
Let's see. If 1.6 is already implemented, how does it make sense to update to 2.0.1? Are the transactions downward compatible?
It's not downward compatible, but there are a lot of advantages to proceed to 2.0.1. For example, the idle fees case is not really possible in OCP 1.6. You need a lot of customization to be able to support that. Also, the tariff and costs. We have another webinar about that during this test event. There are a lot of people interested in that also in California, for example. We have the device model, which will give you the ability to do asset management a lot better, to monitor your chargers. We have the 15.11.8 support. Yeah, so there are a lot of advantages to proceeding to 2.0.1, and it does not have to be so complex as one might think, because you can implement it in several different ways, and it can also be implemented in a very easy way. But it can be very powerful if you also want to do complex things.
Thank you. How can I get more details on the additional information on the cause of suspended EV you have mentioned?
On the what of suspended EV? On the
additional
additional information of the
on the cause of suspended EV.
Cause.
Mm-hmm.
I think this question is a bit similar about the hot battery I already mentioned, because these kind of causes are often hardware related, and these kind of things can be reported via the device model. Because I think in 1.6 the status notification was used a lot for this, to report warning or error informational situations, and now this functionality has been transported to the device model. So there you can set some hardware components like the battery and report the temperature or that it was overheat, and then link it to the transaction via the transaction ID field, which is also contained within that same event message. So that's a way to report additional information, and it's fairly free format, that message. It can contain a lot of information you might want to provide for the CSMS.
Okay, thank you. Let's see. Are the states that you demonstrated required by the specification, and where do I find them?
Of course, OCP does not describe any states, but if you closely look at the requirements, then you see that you indirectly have some kind of OCPP states, because a requirement may mention that you need to perform a certain action or cannot perform a certain action in certain situations, and based on that, it means that you are restricted to follow certain scenarios which are described in the use cases. And the combination of all those use cases sort of indicate that there's some kind of transaction state machine. And that's what I wanted to make you be aware of. And as of now, there's not more information about this, but we want to provide some more detailed information also via this webinar on how to handle this during your implementation.
Okay, let's see. Does the state transition, this one. Does the state transition model define the internal states that a charging station should have?
No, it does not define internal states, because there are a lot more states than the transaction states that you need to take into account. A lot more, for example, hardware related states. And I'm not a charging station implementer, so I'm not aware of those states, but this was mentioned during the technical working group that if you want to create a charging station, a full charging station state machine, a lot more has to be need to be taken into account.
Okay. One question. Nice model. Compliment. Is it intended to be shared, e.g. for users of the standard to get a better feeling of how it should work, or mainly for OCA internally to validate specification and test cases?
For now, we're using it for the second point, but we are still discussing in the technical working group what we want to do with this simulation, and how we want to proceed with it, if we want to include some things and whether we want to share this.